Here's another example of getting the inverse Laplace transform using completion of the square, and the first shift theorem is also used. Now we can't factorize the denominator here, so we can't break it down into its partial fractions. That would be more straightforward. We could then look up the inverse transform of the two partial fractions, because those are in the table. So here we have to complete the square, so we get half the coefficient of s. Half of plus 2 is plus 1, so we write s plus 1 and square it. If we do that, we get s squared plus 2s plus 1. So we have to add on 4 to get to 5. Now if we look at the denominator, we have a function of s squared plus a constant. So if we go to the table, we can see that that's the case for entries 5 and 6. The denominator has a function of s squared plus a constant for both of these. For this one here, the number on top is the square root of a squared. And for this one here, we have to have s on top. So now we don't want s to appear here on the right hand side. We want s plus 1. So we want to replace this s in both of these with s plus 1. You'll see now in a minute why we actually need both of these, not just this one here, which has s on top. First of all, we take out the 4, because we don't see any 4 appearing on top here, of course. And that leaves us with s on top. But we have to have s plus 1, because we have an s plus 1 in the denominator. So we have to change s to s plus 1, so we have to add 1 onto s, but we have to compensate, of course, by subtracting 1. So now you can see why we need this rule as well, rule 5, because we're going to get a constant on top as well as s on top. So we can write this single fraction as two fractions. We take s plus 1 over the denominator, and then we take minus 1 over the denominator. Now this first fraction here has got the required form. It's got this form here of rule 6. If we just replace s with s plus 1, we can see actually that a squared is 4 for this fraction here. We'll have to apply the first shift theorem to this. As for this one here, we've got a 1 on top. But you can see from rule 5 that the number on top must be the square root of this number underneath. The number underneath is 4. So we must have the square root of 4 on top. The square root of 4 is 2. So we need to put a 2 on top here. But ultimately we want to end up with a 4 on top, because we've taken the 4 outside. 4 times 1 is 4. So if we put a 2 on top here, we have to have a 2 outside. So now this fraction has the form a over s squared plus a squared, where a is actually 2 for this fraction, and we replace s with s plus 1, but the first shift theorem will take care of that. So next we get the inverse Laplace transform. We can use the linearity property to take out the 4, that's just a constant factor, and to take the minus 2 out of this second one here. Let's start with this fraction. It comes from this one here, which we will call f of s, s over s squared plus 2 squared. That means that f of s plus 1 is what we have here. We replace s with s plus 1. From the table, we know that the inverse transform of s over s squared plus a squared is cos of at, where a in this case is 2. So little f of t is cos of 2t times ut. So I've written down f of s plus 1 here. We know that the first shift theorem involves big F of s plus a, where a in this case is actually plus 1. So the first shift theorem tells us that little f of t for this function now, not for this one up here, it's a different f of t now, is e to the minus at, where a is 1, so it's e to the minus 1 times t, times the little f of t that corresponds to big F of s. So to get the inverse transform of f of s plus a, we multiply e to the minus at by the inverse transform of f of s. So we could write the first shift theorem like this if we like. We got the inverse transform of this here. In general, that's f of s plus a. That's e to the minus at times the inverse transform of f of s. Let's do the other fraction. I will call the other fraction f of s. Well, actually, the other fraction is f of s plus 1, but we will start with f of s. It's 2 over s squared plus 2 squared. We can look up its inverse transform. We have it set up so that we can read it from the table. So here it is with a equal to 2. 2 over s squared plus 2 squared. We get sine of 2t times ut. Now here is f of s plus 1. What we're interested in is this here. And by the first shift theorem, the inverse transform of f of s plus 1 is e to the minus at, where a is this number here. See, we compare this to f of s plus a. So plus a equals plus 1, so we get e to the 1t times the inverse transform of big F of s, which is sine 2t times u of t. So that's our result, and if you like, you can factorize e to the minus t out, and we get this. Now, in this next example, we see a case where the denominator has no factors. You won't be able to factorize this denominator, so we can't use methods from previous videos where we get the partial fractions of this and get the inverse transform of two functions which are in the table, which we can read more or less directly from the table. So that approach won't work. So we will have to complete the square of the denominator, and we will end up using the first shift theorem, where s has been replaced with s minus 2 in this case. So half the coefficient of minus 4 is minus 2. If we square this out, we get s squared minus 4s plus 4, and we have to add on 2 to get the plus 6. So what is f of s going to be for this example? Well, it's going to be 3 over s squared plus 2. So instead of s minus 2, we will have s. What's the inverse transform of this here? Well, we see that rule 5 is what we need. We have a constant on top, that's the 3, and we have this constant squared underneath. But of course we can see that they don't match up. We want the number on top to be the square root of 2. So that will make a equal to root 2. So this is what we want, actually. Root 2 squared gives us the 2, but then we have to have the square root 2 on top to compare it with this. But what about the 3? We can't just get rid of the 3. So the 3 comes out, and to compensate for putting a root 2 on top, we have to divide by root 2. So just make sure that these are equal, of course. Now we can use the linearity property of the inverse transform, to take out the 3 over root 2. That's just a constant multiple, and we have to get the inverse transform of root 2 over s squared plus root 2 squared. But of course we have this set up now. A is equal to root 2, so the answer is sine root 2t times ut times u of t. Now let's get back to the problem. So here is f of s. We want not f of s, but as you can see, we want f of s minus 2. So that's 3 over s minus 2 squared plus 2. So now we apply the first shift theorem. Well, we compare this to f of s plus a, and we can see that a is equal to minus 2. So we're going to get e to minus a times t. So e to the minus at, well, that's going to be e to the minus minus 2 times t, or e to the plus 2t. and we know we have to multiply this by the inverse transform of big F of s, which is this here.